Yes, students, hi, a very good evening, everyone, and welcome once again to Om Institute YouTube channel. And yes, guys, for the students preparing for the GATE examination for the upcoming weekend, that is on the 15th and 16th February. So let me tell you, if you're preparing for electronics as well as, in fact, for data science paper, data science and artificial intelligence paper, so there is an important topic, that is vector space, and also within the vector space automatically I will cover subspaces, the span, what is a vector span and what makes a basis of a vector space, what is the dimension of a vector space. Okay, usually these are some of the terminologies that are confusing to the students. Okay, so as per students demand, I thought of taking a separate session, okay, which will only focus on the vector spaces, vector subspaces, vector span, vector basis, and dimension of a vector space. And at the same time, somewhere in between, I will also cover linearly dependent and independent vectors, because that is the foundation required to especially talk about the basis of a vector space. Okay, so that I will cover somewhere in between. Don't just worry about that, but all the concept of dependent independent vectors, okay, will be taken up here, right dear? Okay, yes, very good evening. Come on, update all your friends that the session is now live, and let's get started with the session then. Just a moment. Hello. Just I'm confirming the sound once, just a minute. Okay, I think looks good. Okay. Okay, Balakrishna, you have to enroll for the GATE 26 course. Okay, so you can direct, if you're not able to enroll, you can first of all go to the website ominstitute.live, and if you're not able to enroll through the website, or you can go to the Om Live app, you can directly contact our number 9515694053. Okay, or message me in Telegram, I'll guide you. Right now, let's get started, dear. Okay, with the vector space, span and the basis. Okay, so I hope you are ready. Any doubt you have with any terminology, just keep me updated in the session itself. So first of all, yeah, so before I start the topic, important updates. Yes, the GATE online live course, the fresh GATE 2026 as well as for 2027, the online live course starts tomorrow, that is 8th February. The fee for 1 year 2026 course will be 99.99. For the 2 years 2027 course will be 28,999, right? And as well as at the same time, okay, if you want to prepare for GATE 26 in a dedicated manner offline at our Hyderabad center, you can also join the regular offline course. The first offline course for GATE 26 starts on 24th of February. Okay, the fee is currently priced at 54,999, right? You have downloaded, then you can join through it. Still, if you are facing some troubles, as I told you, you can just contact the numbers 95156940053, right? Okay, yes guys, so now vector space. Okay, of course we are going to talk about real vector spaces. Okay, a real vector space is nothing. See, vector space in simple, the first statement that I should give is nothing but a set of vectors. Okay, it is nothing but a set of vectors. Okay, together with the rules of vector addition and scalar multiplication. Now, what do I mean by this rules of vector addition and scalar multiplication? The first thing you should know that when I'm talking about a vector space, it is nothing but a set of vectors. Okay, like you have set of objects, set of elements. Here I talk about set of vectors in simple. Okay, set of some vectors will be known as the vector space. Okay, but all the vectors must necessarily be of the same size. Okay, you cannot have a set of a 2 cross 1 vector with a 2 cross 3 vector or a 3 cross 1 vector. All the vectors necessarily have to be of the same size. necessarily have to be same space. So that is why now, on being a very clear side, let me define the vector space Rn. Okay, Rn or R power n as you read it. Okay, so it is a set of all the vectors of the same size n cross 1, because only vectors of the same size could be added. Only the vectors of the same size. Suppose if you have a 2 cross 1 vector, okay, and if you have a 3 cross again a 2 cross 1 vector only, okay, you can add them, you can subtract them. Okay, but along with these two, can you add this vector? No, not possible. Vectors of only same size could be added. Okay, so when I say, it is a set of vector with the rules of vector addition, that means if you have any two vectors, u and v, inside the vector space, they can be added. And also following the scalar multiplication. That means you multiply this vector by any scalar number, the resultant is going to be of the same size. Why not? If you multiply it by, suppose, any number 5, what is the resultant vector? 5 2s are 10, 5 into 1, 5. The resultant vector is still of the size 2 cross 1. 2 cross 1. Isn't it? So a set of all the vectors of the size n cross 1, okay, with real components. Okay, so say for example, okay, if you have Rn, which is defined as a set containing x1, xn transpose, okay, that's why, we normally arrange vectors. When I say vector here, normally it means a column vector. So it is set of all the column vectors x1 to xn. See, it is written in the form of transpose means, if you see each and every vector, it is of this kind. x1 to xn whole written like this. This is the n cross 1 vector. It is a n cross 1 vector such that x1, x2, etc., xn all belongs to the set of real numbers. That means all the elements are real. Okay, when you see Rn, okay, when you see this notation Rn, okay, or very clearly, in the standard form, it is written as this format. What is this Rn? See, when I talk about R means real. R here is for real. That means it is a vector whose all the components will be real number, no complex element. And when I talk about n, what is this n? N is known as the dimension. Okay, by dimension right now, I do not mean this dimension n cross 1, but wait for some time, I will define dimension once I talk about basis, once I talk about independent or dependent vectors. Is that clear? Okay, so that is what it is. It is a set of all the vectors of same size n cross 1. I again repeat, it is represented as Rn. R is the set of, R stands for real and n is the dimension. The true definition, the exact definition of dimension, we will define after some time. Okay, so suppose there can only be a set R1. So what is R1? It basically will contain only elements, because if you talk about a vector of size 1 cross 1, when I said Rn, it is the set of vectors of n cross 1 size. So R power 1 becomes set of vectors of size 1 cross 1, and 1 cross 1 means a single element. So what is R? R is nothing but set of real numbers. Okay, if I say R power 1 or simply R, it is nothing but the set of real numbers. Okay, so R equal to R contains those elements x such that x is a real number. It is the set of real numbers simply. Okay, but when I say R power 2, R square, R2, different ways you can read this. It contains the vectors of the size 2 cross 1, okay, which have the elements x and y such that, this is, how do you read this? This is known as such that, okay, such that x and y are real numbers. Okay, so like I generally defined Rn is the set of all vectors of the size n cross 1. Similarly, R2 is the set of all the vectors of the size 2 cross 1, where x and y can be all real numbers. So, what are the vectors that can come inside this? Say for example, 1 minus 1, this is a 2 cross 1 vector. 2, 3, this is a 2 cross 1 vector. It can take any real value. Okay, so it may be of the form 2.538 and minus 1.686, anything. Okay, any such thing can come up. Okay, so all these are nothing but 2 cross 1 vectors. Is that clear? All these are nothing but 2 cross 1 vectors. That is the first point to be noted. Similarly, I can write down R3. Okay, R3 is the set of all the vectors x, y, z, all the 3 cross 1 vectors x, y, z, such that x, y, z are real numbers. Okay, so that means it is basically a set of all real 3 cross 1 vectors. Okay, all real 3 cross 1 vectors, what I mean is all the elements x, y, z can take any real value. Again, okay, it may be positive, negative, 0, integer, fractional, any value. Okay, so it can be written in the form of 2, 0, minus 1. This is one of the vectors. Okay, this can be one of the vector which belongs to R3. There can be another one like this, minus 3, 2.8, and 4.9. This is another vector lying inside the R cube, inside the R3. There can be vector of the form 0, 2 root 2 and 5 root 7, any such vector where x, y, z can take any real values. So basically set of all 3 cross 1 real vectors, okay, is what is represented as R3. Is that clear? So this is R3, this is R2. In general, we define the vector space Rn. Okay, collection of all the vectors of the same size, that is n cross 1, so that because they are of the same size, so any two vectors inside the vector space can be added. Okay, can be added. And if you multiply any vector by any scalar number, again I show you, if I multiply it by any scalar number, what the elements will become? Kx1, kx2, etc. up to kxn, but the resultant vector is still of the size n cross 1. Okay, so this is what is the basic, terminology. We are just going through some basic terminology. Slowly we'll go towards higher concepts, and slowly we will see what type of questions are there, in an exam like GATE, and what can be expected also in the exam like GATE. Okay, so I hope this terminology is clear first of all to all of you. That is Rn. Okay, what do I mean by Rn? So, if I say R4, okay, if I say R4, it is set of all the real vectors of the size 4 cross 1. Suppose it has 4 elements, x1, x2, x3, x4. All x1, x2, x3, x4 can take real values. Any real values, maybe positive, maybe fractional, maybe negative, maybe 0, any real value, right? Okay, now let's understand another example here. Let's understand another example. Okay, now you have to consider a vector space R3. Okay, so what is vector space R3? It is a collection of all the real vectors of size 3 cross 1. Clear? Of the size 3 cross 1. Okay. And now consider a plane which is passing through origin, which is as shown. Okay. So I have taken a plane which passes through origin. What is normally the equation of any plane? Normally the equation of any plane is represented as ax plus by plus cz equal to d. Okay, equation of any plane. But if it is passing through origin, it could be represented as ax plus by plus cz equal to 0 if a plane is passing through origin. Okay, so here let's take a simple equation. Suppose there is a plane, okay, x plus y plus z. I have assumed ABC as 1. Okay, there is to be assumed any plane. To understand the concept, okay, what is the concept that you have to focus? The plane is not that important, but yeah, there is some plane passing through origin. Suppose the equation of the plane taken is x plus y plus z equal to 0, correct? Now, if you add any two vectors in P, the sum remains in P. Now, can we take any two examples, any two examples of the vector which lies in this plane? Okay, any vector lies in the plane such that x plus y plus z equal to 0. That is the equation of the plane. Say for example, if I take a vector, you can take a vector like this, okay, 2, 1, 2, minus 1 and minus 1. The sum of x, y, z should be 0, correct? You can also take a vector here, 1, 0, minus 1. This also lies within this plane. You can also take a vector here, 1, minus 1 and 0. This also lies in this particular plane. Is that clear? Now, dear, what you can notice is when you add these two, 1 plus 1, 2, 1 plus minus 1 is minus 1, minus 1 plus 0 is minus 1. Okay, so dear, when you add these two vectors, okay, the resultant, this is the resultant. Okay, so let me say this is x1, this is some vector x2, and this is some vector, suppose x. Okay, when you add x1 plus x2, the result is x, which is also in the same plane. Is that clear? Which is also in the same plane. Okay. Now, if I multiply any vector in P by any scalar number, suppose if I take up, say for example, 3x1. If I multiply any vector, suppose that vector is x1, okay, any vector in P by any scalar number, see what is the result? 3x1. What is the result? 3x1. 3x1 looks like 3, 0, minus 3. Is this also lies in the plane? If any vector or if any point lies in the plane, it should satisfy the equation of the plane. So x plus y plus z, 3 plus 0 plus minus 3 equal to 0. Perfect. So this also lies within the same plane. So if we multiply any vector in P by any scalar number, the resultant vector remains in P. Now here we say that important and very important point. Okay, here we say that the plane P here is a vector subspace of R3. Now let us define what is a subspace. See, normally for any set we have subset. What is a subset? Any set which can be derived from the original set. But here subspace, of course, subspace is any subset of the vector space, but with some conditions. Those conditions are important. Not every not every subset of a vector space can be called as a subspace. So listen to me, what is a subspace? Here as an example, I'm telling you the plane P is a vector subspace of R3. Okay, what is a vector subspace? What is the conditions so that a particular set of vectors can become a subspace of R3 or of any vector space Rn? See here, a subspace of vector is a set of vectors including null, including origin as well, that satisfy the two requirements. What are the two requirements? So suppose if V and W are vectors in the subspace and C is any scalar, then V plus W is also in the subspace. Okay, now listen to me, if V and W are vectors in the subspace, like x1 and x2 are the vectors in subspace, automatically x1 plus x2 is also in the subspace, right now? Right? Okay, so here, if V plus W is also, if V and W are vectors in the subspace, then V plus W is also in the subspace. And if C is any scalar number, then C into V should also be in the subspace. If V is in the subspace, C into V should also be in the subspace. Like I told you, if this is x1, okay, this is 3x1. Okay, this is 3x1. Clear everybody? Clear everybody? Okay, so if x1 is in the subspace, 3x1 or any cx1 or any cv should also be in the subspace. In moral of the story is, okay, any linear combination. Now, like if V is in the subspace, CV is in the subspace. If W is in the subspace, DW. Let's take any coefficient D. DW should also be in the subspace where D is a scalar number. Okay, so when I say CV and DW are in the subspace, then any addition or even subtraction of them, okay, will remain in the subspace. Okay, will remain in the subspace. So that means any linear combination of V and W, okay, also remains in the subspace. This is the condition, okay, to be fulfilled by a subspace. That means, again I repeat, if there are two vectors V and W in a subspace, then any linear combination of it should also be in the subspace. What is a linear combination? CV, okay, plus or minus DW. CV plus or minus, you all know linearity always includes two things. One is additivity, one is scaling. Okay, this is what is additivity. If two vectors, okay, are vectors in the subspace, then, you know, if V and W are vectors in subspace, V plus W should also be in the subspace, additivity. If V is in the subspace, C into V, okay, that is known as scaling, multiplying by a scalar number, that is known as scaling. So CV should also be in the subspace. Generalizing it, if V and W are vectors in the subspace, then CV plus or minus DW should also be in the subspace. Okay, then only that set of vector, then only that, you know, subset of the vector space will be known as a subspace. Now I'll show you with example, you know, how sometimes there is a subset which may not be a subspace. Okay, let's understand here. First of all, consider the vector space R2. So let's taking a simple example. You know, R2 means set of all. Okay, as I told you earlier also. Okay, set of all. You know, vector space R2. What is this vector space R2? Set of all real vectors of size 2 cross 1. Set of all the real vectors of the size 2 cross 1, isn't it? Set of all the real vectors of the size 2 cross 1. Okay, set of all the real vectors of the size 2 cross 1. Now, what does it mean? Okay, when I say all the real vectors of the size 2 cross 1, okay, that means the set, as I defined earlier also, set containing the vectors x, y, such that x belongs to real number, y also belongs to set of real numbers. X and y can take any real value. Any real value means minus infinity to infinity, plus infinity to minus infinity to infinity. Y also can be from minus infinity to infinity. Okay, now consider the set S. Okay, which contains those vectors, those 2 cross 1 vectors x, y, such that x is greater than 0, y also greater than 0. That means it contains set of all the points. If I take it in a plane, okay, what can I say here? Okay, R2 here in short is set of all points in the two-dimensional xy plane. Can I say? In the two-dimensional xy plane. Okay, suppose you consider this xy plane. So R2 is a set of all the points that can lie in the xy plane. R2 is a set of all the points that can lie in the xy plane. But what is the set S? First I spoke about R2. Now what is the set S? Set contains all the values of x, y, okay, such that x and y are both positive. That means If x and y both have to be positive, that means the point will be in the first quadrant. That means set of all the points, okay, in the first quadrant. Now it looks like my R2 is the entire two-dimensional xy plane, and the set S is the first quadrant. Okay, the set S is the set of all the points lying in the first quadrant. Set S is the set of all the points lying in the first quadrant. Now my question is S a subspace of R2? Okay, I told you the requirements of R2. So what I will do is, let's take this picture here. Let's understand this picture here. Okay. Okay, so as I told you, what is R2? R2 is this entire two-dimensional, going from minus infinity to plus infinity, okay, along the x-axis also, along the y-axis also. That is R2. But when I told about set S2, what is the set S2? S2 is the set of all the points xy such that x is positive and y is also positive. So this is the set S, okay, which looks like a subset of R2. But my question is, does it satisfy the necessary condition to be defined as a subspace of R2? And what I told you, if there are any two vectors in a subspace, their addition should also be in the subspace. Or if there is any one vector v in the subspace, scaling c into v should also be in the subspace, where c can be any scalar number. Now, okay, if I talk about set S, 1, 1 is a valid point. Okay, 1, 1 is a valid point. Suppose this is v. Suppose this is a vector v. Okay, now what about minus 2v? By minus 2, let's take an example cv. What about minus 2v? Additivity will be okay here. Okay, but will scaling also be okay? See, what about cv? Take an example. C equal to minus 2. Suppose I take c equal to minus 2. So what is minus 2v? If this is v, minus 2v is minus 2, and this is a third quadrant point, isn't it? This is a third quadrant point. That means it is not in S. What I told you, if v is in the subspace, cv should also be in the subspace. Then only, the set of all those points can be classified as a subspace. So very clearly, okay, v is in the set S, but cv is not in the set S. So S not a subspace. S is not a subspace. Is that clear, everybody? The set S is not a subspace. It is not a subspace, right? Okay, so I hope now the definition of subspace is clear to you. I repeat once again. Okay, what is the subspace of a vector? It is set of those vectors, okay, that satisfy the two requirements. If v and w are vectors in the subspace, v plus w should also be in the subspace, and c into v should also be in the subspace. Okay, so as I've shown you here, okay, this first quadrant, it looks like, okay, it is a subset, but it will not be called as a subspace. So S is not a subspace. Okay, hope that is clear. Now let's move ahead. Okay, this example was taken so as you understand what is the meaning of a subspace. Okay, so as I've shown you here. Yeah, so this example was taken so that you understand what exactly do you mean by a subspace. Okay, what can be a subspace, what cannot be a subspace. Okay, now let's come to the next term, span. Okay, span and basis. Okay, what is the vector span? First of all, understand this. Okay, all the keywords are important. All these keywords are important. So see, suppose you have the vectors v1 to vn. Okay, there are some vectors v1 to vn. Set of all linear combinations of these vectors, is called the span of these vectors, and the span, of course, is also a vector space. Now let me explain you with example. Okay, as I told you, the set of all linear combination, this point is important. Okay, the set of all linear combinations of these vectors, which vectors v1 to vn, is set to form a span of these vectors. So now, what is the span of the vector space? Okay, so what I have taken a vector space. Let me write it this way. I have taken a vector space V, which contains two vectors v1 and v2. Okay, what is the span of this vector space? So as I told you, what do you mean by span? Okay, span is a set of all linear combinations of the vectors in a given vector space. Okay, that means if v1 and v2, what do you mean by linear combination? As I told you, linearity always means two things, additivity and scaling. So what can be the linear combinations of these vectors? What can be the linear combinations of the vectors v1 and v2? It can be written as simply a1 v1, okay, plus or minus a2 v2, okay, plus or minus a2 v2. Suppose there can be several examples, like if you take a1 a2 both 1, okay, a1 a2 both 1, okay, so it can be v1 plus v2, okay, or with minus sign it may be v1 minus v2, okay, or it may be 2v1 plus v2, or it may be any other case like v1 minus 4v2, okay, or it may be minus v1 minus 3v2, etc. That means if I write down the values, what is v1 plus v2 here? 1 plus 3 is 4 and 2 plus 4 is 6. Okay, right. Then v1 minus v2, 1 minus 3, okay, is minus 2 and 2 minus 4 is minus 2. Right. Then next I have taken 2v1 plus v2. Okay, so 2 plus 3, this is 5, and then 2v1, 4 plus 4, 8. Next, okay, v1 minus 4v2. Okay, so 1 minus 12, minus 11, and 2 minus 16, minus 14. Next example, I have taken minus v1 minus 3v2. Okay, so v1 plus 3v2, 3, 9, minus, and then 2 plus 3 into 4, 2 plus 12, minus 14, then it should be. Clear, everybody? Okay, this is what it is. Okay, so a set of all linear combination of these vectors is called a span of these vectors. Okay, so when all such combinations, how many such combinations? There can be infinite such combinations, isn't it? There can be infinite such combinations. Okay, but when all these combinations, that means all these vectors, when placed within a set, that set is known as the vector span. Span of what? Span of the given vector space. Is that clear, everybody? Let's learn with more examples. The story doesn't stop here. Okay, so firstly, in a simple way, I told you the set of all linear combinations of the given vector, suppose v1 to vn, is called the span of these vectors. Like I initially took two vectors v1, v2. The all linear combinations can be written as a1 v1 plus or minus a2 v2. Okay, several examples I've written, and there can be endless combinations that you can make. So what I want to show you that all of these vectors, okay, will come in the span of the vector space v2. They span this given vector space. Okay, now a random check here, whether or not the given vector 20, 26 belongs to the span, same number, same vectors I have taken, okay, belongs to the span v1, v2. Okay, same two vectors I have taken. Now how do you check, okay, whether any vector belongs to the span? So what comes in the span of v1, v2? Again, revise. What comes in the span v1, v2? What comes inside the span v1, v2 is all the linear combinations of v1 and v2. So this also belongs to the span if this vector, what is the vector? 20, 26. Okay, should be a linear combination. Okay, should be a linear combination, that is a1 v1 plus a2 v2. Okay, let me write plus only. If it is minus, automatically a2 value will come as negative. It should be expressible like this. Okay, let us see whether it is expressible like this or not. So 2026 is equal to a1 v1. Okay, what is a1 v1? So a1 and 2a1. a1 multiplied by v1 plus a2 v2. a2 multiplied by v2, so 3a2 and 4a2. Okay, two vectors of same size can be added. Okay, so the first element is a1 plus 3a2 and the second element is 2a1 plus 4a2. That means this gives me two equations. If I am able to solve the equations and get the value of a1, a2, yes, then my story is done. Okay, so what can I say here, dear? a1 plus how much? 3a2 should be equal to 20, and 2 of a1 plus 4 of a2 equal to 26. Okay, now dear, you can divide this by 2 easily, na? a1 plus 2a2 equal to 13 then, if you divide by 2. Okay, and then when you subtract the first equation, or from first you subtract third. Okay, from first, suppose this is 1, this is 2, and this is 3. Okay, when you subtract 1 minus 3, okay, when you subtract 1 minus 3, you get the value of a2. How much? 20 minus 13, 7. Okay, and then put the value of A2 equal to 7 in the first equation. So from the first equation, what is A1? 20 minus 3A2. So 20 minus 3 into 7 is minus 1. So A1 is minus 1. Yes, we have been successfully able to obtain, okay, two scalar numbers A1 and A2. That means what can I say here? What can I say here? I can say that this given vector, okay, suppose x, okay, this given vector x can be written as A1. What is A1? Minus 1. Can be written as minus of V1 plus 7V2. Okay, this vector x is a linear combination. Listen to me. This is a linear combination. This vector is a linear combination of V1 and V2, and hence belongs to the span of V1, V2. Okay, again I repeat, what is the span of vectors? The span of vector is the set of all linear combinations of the given vectors. Okay. That's what I'm telling, na Durga. That's what I've explained you. What is span V1, V2? Have a look into this example. Span of V1, V2 is the set of all the vectors which are linear combination of V1 and V2. Okay, which are linear combination of V1 and V2. That is A1, V1 plus or minus, or 2. If you want to understand simply, let me call it as plus only. Doesn't matter. A2 can be negative then. Okay, if you want to form a span of the vector space V1, V2, it is the set of all vectors which are the linear combination of V1, V2. What can be the example? I again repeat, V1 plus V2, V1 minus V2. A1, A2 can take any value, na? Maybe positive, maybe negative, maybe 0 also. Okay, then 2V1 plus V2, V1 minus 4V2, minus V1 minus 3V2. Like this, you can form infinite possibilities. Okay, set of all linear combinations of V1 and V2 is known as the span of this given vector space. Is that clear? Then next I told you, given any vector x, okay, whether it belongs to the span V1, V2. Now what should come in the span V1, V2? What should come in the span V1, V2? Set of all linear combination of V1, V2. That means if x belongs to the given vector space, then this x should be written as linear combination of V1, V2, A1, V1 plus A2, V2. What I did, I substituted the given vector x, I substituted V1, V2, and I got two equations in two variables. I am able to find the values of A1 and A2. Okay, that is minus 1 and 7. That means x is equal to minus V1 plus 7V2. That means x is a linear combination of V1 and V2, and hence the x belongs to the span V1, V2. Okay, hope that is clear to you. And now let's move ahead to the next thing. Okay, consider the vector space V. Now same V, 1, 2, 3, 4. Okay, 1, 2, 3, 4. Okay, does the V span R2? Okay, does it span R2? Now what is the meaning that does V span R2? Okay, does V span R2? Okay, how do you span R2? What is R2? Set of all 2 cross 1 vectors. All real 2 cross 1 vector. All means all. Anything from minus infinite. X can be any value minus infinite to infinite. Y can be any value from minus infinite to infinite. Clear? Okay. So, does this vector space span R2? Okay. How do you check this? How do you check this? How do you check this? So, now understand. Okay. If this span R2, let me form another set here. Okay. So, what is R2? Let me redefine for you. What is R2? Set of all real, again I repeat, set of all real 2 cross 1 vectors, right? X, Y. Okay. Where X belongs to R and Y also belongs to R. X and Y can take any real value from minus infinite to infinite. Okay. Now, does the vector space V span R2? Okay. That means when I take these two vectors, what are the two vectors? 1 and 2, 3 and 4, and X and Y. Okay, X and Y. Let me write like this. Okay, let me write like this. Now what I do is, for better understanding, let me write them in the form of a matrix. Okay, form the matrix. Form the matrix. What type of matrix you will form? Let me name the matrix as A. Okay, what is the matrix? 1 and 2, 3 and 4, and X and Y. Okay, can you talk about the rank of this matrix? What is the size of this matrix? 2 cross 3. Okay, when it is a 2 cross 3 matrix, what we know about the rank? I hope The definition of rank is clear to you. Okay, rank, which is also equal to number of independent rows or independent columns, and rank is also equal to the largest non-zero minor, the size of the largest non-zero minor. Okay. The rank of A, because it is a 2 cross 3 matrix, rank can be less than or equal to 2. Okay, the largest possible minor is 2 cross 2. You cannot have a 3 cross 3 minor. The largest possible minor will be 2 cross 2. Okay, now whether that 2 cross 2 minor is 0 or non-zero. Okay, let me check any 2 cross 2 minor. Suppose if I take up this 2 cross 2 minor, 1, 3, 2 and 4. 1, 3, 2 and 4 and check the determinant. Cross multiply 4 minus 6 and this is not equal to 0. That means I have a 2 cross 2 minor. I have a 2 cross 2 minor which is non-zero. Okay, and if there is at least one 2 cross 2 minor which is non-zero, rank is said to be 2. Okay, that means I am able to confirm that the rank of the given matrix is 2. Now, rank is also equal to different ways, of understanding rank. Okay, different ways of understanding rank of a matrix. Okay, it is equal to largest order of non-zero minor of the matrix. Non-zero minor of the matrix. What is the largest order or largest size of the non-zero minor of the matrix? Okay. Another way to understand that, the rank is also equal to the number of linearly independent columns of the matrix, or it is also equivalent to the number of linearly independent rows of the matrix. Number of linearly independent rows of the matrix. Correct. This is what we know about the rank. Okay. So in this video, I'm not covering the entire linear algebra, but only about vector space, span and basis. Okay. And since GATE exam is very close, so I hope that basic idea about rank you have. Okay. So I have calculated a 2 cross 2 minor. That is the largest minor, and that is in fact non-zero. Okay. So what is the largest size or largest order of a non-zero minor? That is 2 cross 2 here, or simply we call it as 2. So rank of this matrix is equal to 2. Now if the rank is 2, I can conclude that this given matrix will have 2 linearly independent columns. How many linearly independent columns? 2 linearly independent columns, correct? It can have 2 linearly independent columns. Okay, so definitely the third column, I am able to see 3 columns here. 100% third column is dependent. 100% third column is dependent. Okay, now let me name these columns as C1, C2, C3. Okay, which 2 are independent? You can choose any 2 as per your choice. Suppose I call these 2 as the independent columns. Okay, I choose these 2 as the independent columns. So what is my third column? That means the third column C3 should be dependent on the first and second. How it is dependent on first and second, that you don't need to find out, but yeah, it may be something written as A1 C1 plus A2 C2. Okay. Now what is the column 3? Now come to the story again. What is the column number 3? Column number 3, okay, is this vector, is this 2 cross 1 vector x and y, where x and y can take any value. Okay, x and y can take any value. Okay, now my question is, does the given vector space span R2? How do you span R2? Spanning any set or any vector space means it is the set of all linear combinations, okay, of that particular space, of that particular vector space. Okay, so what is the vector space? XY. Okay, so see, yes, by using these two and the linear combination of these two, I am able to write down all the vectors x and y, because that is the column C3. And hence I can say that V span R2. Okay, V span R2, or in other ways, R2 is spanned by V. It is spanned by V. Okay. Now let me take the difference. Consider the vector space 1 minus 1, 2 minus 2. Does V span R2? My question is same. Does this V span R2? Okay, or is the R2 spanned by V? Okay, what are the vectors inside V now? What are the vectors inside V? Okay, slight change is there, and once again I'll tell you the same story. Form the matrix A. Okay, what is the matrix A? How did I form the matrix A? Okay, first write down the given two vectors, okay, and then write down, okay, the R2 space, the R2 vector space. So what are the given two vectors? 1 minus 1, 2 minus 2, x and y, x and y. Now dear, okay, now dear, come here and listen to me. Okay, come here and listen to me. Okay, now what can I say here? What is the rank of this matrix? Okay, what is the rank of this matrix? Definitely this 2 cross 2 minor is 0 this time. Cross multiply, na? Minus 2 minus of minus 2, 0. Okay, but what about this 2 cross 2 minor? I don't know x and y. X and y can take any value. Okay, so for better understanding, okay, let me convert it to the echelon form. So if you just add R1 plus R2, okay, and let's say R2 is replaced as R2 plus R1, R2 plus R1. Okay, so how the structure will now look like? 1, 2x and minus 1 plus 1, 0, minus 2 plus 2, 0, and this is x plus y. Y plus x or x plus y. Okay. Now dear, say by chance if x plus y is also 0. Okay, now there are two stories. If x plus y equal to 0, if x plus y equal to 0, okay, then the entire second row is 0. I have only one row or one independent row. Then the rank of the matrix, then rank of this matrix will become 1. Okay, let's say again this is the matrix A. But dear, if x plus y is not equal to 0, suppose any value you take for x and y such that x plus y not equal to 0, because what is xy? Okay, xy is coming in the vector space R2. Okay, let me again keep writing. It is set of all 2 cross 1 real vectors. It is the set of all 2 cross 1 real vectors x and y such that x and y can take any real value. Because x and y can take any real value, x plus y may be 0, may not be 0. So second story, suppose you take x and y such that x plus y not equal to 0. In this case, dear, in this case, rank of A will become how much? Suppose you have any non-zero element here. Suppose you have any non-zero element here. Suppose 2. Then when you take this 2 cross 2 minor, okay, this is going to be 4 minus 0, and 4 minus 0 is 4. That means non-zero. So you will have a 2 cross 2 minor which is non-zero, and hence rank will be 2 na. You will have a 2 cross 2 minor which is non-zero, and hence rank will be 2. Okay, so rank of the matrix will be 2. Okay, now if rank is 1, we have one independent column, okay, and two dependent columns. But here, okay, here when rank is equal to 2, you have only one dependent column. Okay, which one dependent column? Which one dependent column? Definitely, okay, see, definitely, if you notice this relation, okay, this is column number 1, this is column number 2, this is column number 3, and already column number 1 is equal to twice of column number 1. Column number 2 is twice of this, right? 1 into 2 minus 1 into 2. Is that clear? The column number 2 is twice of column number 1. The column number 2 is twice of column number 1. The one dependent column is there 100%. When I say rank equal to 2, okay, there are two independent columns. There are two independent columns. That means there is one and only one dependent column. There is one and only one dependent column. And what is that one dependent column? C2 is twice even. That means C3 will not depend further. Okay, that means there cannot be any relation for C3. You cannot write down the vectors of R2 using C1 and C2. What is the meaning of spanning R2? That means every vector in R2. What is every vector in R2? Is XY. Every vector in R2 should be represented by a linear combination of V1 and V2. That will not be possible if rank is 2. Okay, if rank is equal to 2. Okay, so what is there? It may span, may not span. So there is no maybe or may not be condition. What I generally say, it is not able to span. It is not able to span R2. It is not able to span R2, right? Okay, so rank is not fixed here. Point is, rank is not fixed. Okay, you should have a fixed value of rank for any value of xy. Let me take you back towards the previous example. Okay, previous example, any value of x and y you take. But when I calculate this 2 cross 2 minor, which is independent of xy, this 2 cross 2 minor itself is non-zero, and hence rank is fixed at 2. Okay, rank is fixed at 2. So when you get the fixed value of rank, okay, independent of xy, okay, this is the fixed value. Yeah, sorry here. This is the fixed value. Independent of x and y. Okay, so then in that case, the x and y can be written as linear combination. X and y means column C3 can be written as linear combination A1 C1 plus A2 C2. That means vectors in the R2 can be represented by the linear combinations of the vector in V. That means the vector V span R2 or the vector space R2 is spanned by V. Okay, once again I repeat. When I say the statement R2 is spanned by V, what does it mean? R2 is spanned by V. That means every vector in the R2 should be expressed, can be expressed as the linear combinations of the vector inside V. Okay, let me write down this one very clearly. When I say R2 spanned by V, when I say there is a term R2 is spanned by V, what does it mean? What does it mean? See, this is all about understanding the language so that, questions you understand. R2 is spanned by V. It means that every vector, it should mean that every vector, okay, which belongs to R2, okay, can be represented as a linear combination of, what? Of the vectors in V. Or let me generalize. If I say Rn, okay, every vector in Rn can be represented as a linear combination of the vectors in V. Okay, can be represented by the linear combinations of the vectors in V. Okay, right? Now let's move ahead. Okay, let's move ahead. Now, in this first example, the R2 is spanned by V. Okay, yes, the answer is yes. Second example, does V span R2 or is the R2 spanned by V? No. Okay, no, as I've shown you. Okay, when the rank is not fixed, then spanning will not occur. We cannot always say that the C3 is a linear combination of C1 and C2. Is that clear? So the difference in the two cases is here the vectors that I have taken, now you call it as C1, C2 or any vectors V1 and V2, they are itself dependent on each other. Or they are scalar multiple of each other, 1 into 2 and minus 1 into 2. Okay, whenever the two vectors itself are dependent or multiples of each other, okay, then those two vectors cannot span R2. Okay, so listen to a very, very important note. Any two vectors in R2, this is about R2 first statement, any two vectors in R2 that are not scalar multiple of each other. Not scalar multiple of each other means what? Any two vectors in R2 that are not scalar multiple of each other, that means they are not dependent on each other. They are not linearly dependent on each other. If they are not dependent, what they are? They are independent. As I told you, there is one more thing I will tell you separately, how to identify dependent and independent vectors. Okay, any two vectors in R2 that are not linear dependent on each other, that means they are linearly independent. Okay, so if there are any two vectors in R2, okay, which are linearly independent, will span all of R2. That means all vectors of size 2 cross 1 can be represented as a linear combination of any two vectors which are linearly independent. Clear? Now, any three vectors in R3, extending it, any three vectors in R3 that are linearly independent will span all of R3. If you want to extend this concept, any n vectors in Rn, but what n vectors? That are linearly independent. Okay, that are linearly independent will span all of Rn. Okay, will span all of Rn. Hope that language is clear to you. Will span all of Rn. Okay. Okay. Now we will come to, this is important point. Now next is, let me define the basis. But before I go to basis, okay, one or two simple examples, and then let's also talk about the dependency and independency in detail. Okay, but first let's take another example here. Consider the vector space V. Again, the same two vectors, 1 minus 1, 2 minus 2. Does this V span the set X? I'm not talking about spanning R2. I'm talking about spanning any set X. Okay, which X? which contains all the elements, all the 2 cross 1 vectors x and y, such that x plus y equal to 0 with the condition x plus y equal to 0. With the condition x plus y equal to 0. So what is the method I told you, dear? What is the simple method I told you? We will form a matrix. We will form a matrix where we will write down the first vector as the first column, second vector as the second column, and okay, the vectors inside the given set. What is the vectors inside the given set? Okay, x and y. But in the previous example, okay, the vector xy belongs to the R2. That means x and y can take any real values. But here, x plus y can only take 0. The sum of x and y should be 0. The sum of x and y should be 0. So because x plus y is 0, so y can be represented as minus x. So better write it like this: 1, 2, x. Minus 1, minus 2, minus x. Now that very clearly means here that the second row is nothing but negative of R1. There are only 2 rows because it's a 2 cross 3 matrix. There are only 2 rows. Okay, but second row is dependent. Second row is dependent on the first row. Okay, so how many independent row? How many independent row? Only one independent row. Okay, so rank of the matrix will be 1, which is fixed. No if, no but. No if, no but. The rank is fixed. And only one independent row also means that rank is 1, which also means that the matrix has only one independent column. Only one independent column. If it has only one independent column out of the 3, so tell me how many are dependent columns? How many are dependent columns? That means there are 2 dependent columns. That means there are 2 if only one independent. So you can say that there are only 2 dependent columns. There are 2 dependent columns. What are the 2 dependent columns? See here. Okay, suppose this is C1. Suppose this is C2. Suppose this is C3. Okay, if you say C1 is your independent column, so C2 is twice of C1. Yes or no? C2 is just twice of C1. 1 into 2, 1 minus 1 into 2. Similarly, we can write down C3 is nothing but x of C1. C3 is nothing but x of C1. 1 into x minus 1 into x will give you C3. So these are the 2 dependent columns. Okay, these are the 2 dependent columns. That means now, can I write down? Now my question is C3, okay, is C3 represented as sum A1 C1 plus A2 C2? Yes, it can be represented as A1 C1 plus A2 C2, where I told you A1 A2 can take any scalar value. The A1 here is equal to value of x and A2 here is 0. A2 here is 0. Okay, yes, it can be represented as this way. That means, okay, these columns C1 or C2. Okay, these columns C1 or C2, which are the given vectors V1, V2. Okay, the vectors inside this set X, listen to me, the vectors in the set X. Okay, this gives me a conclusion. Let me write down here. The vectors in the set S can be represented by a linear combination. All vectors in the set S can be represented by, okay, linear combinations of the vectors in the set V. Okay, vectors in the set V. Okay, vectors in the set V. That means, okay, your set V will span the set X. So what I say here, okay, the V spans the set S, or other way, the set S is spanned by the vector space V. It is spanned by the vector space V. Okay. One more example. Now consider the vector space 0, 1, 2 and 1, 1, minus 1. Only 2 vectors are there, but they are 3 cross 1 vectors. Okay. For what value of k, the vector 1, k, 7 belongs to the span of V. Again, I've taken this example earlier with the 2 cross 1 vector. Okay. For what value of k, this given vector belongs to the span of V. Now, if it belongs to the set V, okay, let's say this is X and these are V1 and these are V2. X belongs to span of V. Span of V. What is V? V is a set containing the two vectors. Now, any vector belongs to the span of V1 and V2. What is the meaning of span V1, V2? Span of V1, V2 is the set of all linear combination of V1, V2. Okay. If X can be written as A1, V1 plus A2, V2. If it can be written as A1, V1 plus A2, V2. If it can be written as A1, V1 plus A2, V2. Correct? Okay, so let's do this calculation, whether this is right or wrong. Let's do this calculation. So what is X? 1K7. Okay, should be equal to A1, V1. Now what is A1, V1? A1 into 0, 1 minus 2. Sorry, 0, 1 plus 2 plus A2 into V2. That is 1, 1 minus 1. Okay, now firstly, okay, 1K7. 1K7 is equal to how much? A1 into 0 plus A2 into 1. So that is only A2. A1 into 1, A2 into 1. So this is A1 plus A2. And next, 2A1, okay, minus of A2. 2 into A1 minus of A2. Minus of A2. Now from here, what are the comparisons you are able to get? Okay, you are able to first compare and say that A2 is equal to 1. First element A2 is 1. Then 2A1 minus A2 should be 7. 2A1 minus A2 should be 7. So what is the value of A2? A2 is 1. Okay, so 1 goes here. A1 is 8, so A1 should be 4. Then what is the value of K? K should be A1 plus A2. A1 plus A2 becomes 5. A1 plus A2 becomes 5. Okay, A1 plus A2 becomes 5. Is that clear? Is that clear? Okay, another method. Okay, like this is method number 1. This is method number 1. Another simple method. Another simple method. X belongs to span of V1, V2 if X is equal to A1, V1 plus A2, V2. Okay, one way is I calculated A1 and A2. Okay, second way, method number 2. Method number 2. Okay, again form the matrix. Okay, with the given vector V1, V2, X. Okay, but what is X? A1, V1 plus A2, V2. Okay, that means there is a matrix. There is a matrix having dependent columns. There is a matrix having dependent columns. And here by the basic determinant property. Now because you form a 3 cross 3 matrix, you can talk about the determinant. You can talk about the determinant. If I talk about determinant of A, let me write down the numbers. What is V1? 0, 1, 2. What is the V2? 1, 1 minus 1. And what is the X? 1, K and 7. Is that what is given? 1K7, correct. Now this has dependent columns. Okay, and because dependent column, okay, determinant must be 0. Any determinant which has dependency in rows or dependency in column, the determinant value is 100% 0. So if the determinant value is 0, first element is anyway 0, then minus of 1 into 7 minus 2K and plus of 1. Okay, cross multiplying minus 1 minus 2, this must be 0. Okay, so minus here, minus 7 minus plus 2K and this is minus 3, okay, equal to 0. So 2K is equal to the 3 plus 7, that is 10, and K equal to 5. Same answer. K equal to the 5. Same answer. Okay, K equal to 5. That is the same answer. So these two simple methods you can apply. Either you take the determinant equal to 0, okay, or if any vector belongs to the span of V1, V2, that means, okay, what is the span of V1, V2? Again and again I repeat, span of V1, V2 is the set of all the vectors which are linear combination of V1 and V2. That means X should be a linear combination of V1, V2. That is A1, V1 plus A2, V2. Solve the equation here. And first we got A1, A2 and then we got the value of K, which is A1 plus A2. Okay, hope this is clear to you. Hope both the methods are clear to you. Okay, this is what is the concept and this is a simplified method. Okay. Now dear, as I told you before this one, I told you simple points that, okay, any two vectors in R2, okay, which are linearly independent. First I told you which are not multiples of each other, scalar multiples of each other. That means which are not linearly dependent on each other. That means which are linearly independent will span all of R2. I have shown you the supporting examples. Okay, let me again repeat. First I took an example of these two vectors 1, 2, 3, 4. Okay, where if this is a vector v1, this is the vector v2. Okay, v2 cannot be written as cv1. They are not scalar multiple of each other, because if they were scalar multiplied, so this is 1 into 3, but then 2 into 3 should be 6 here. If this was 6, then they are scalar multiples. Okay, so first I took two vectors which are not dependent on each other, that means which are independent, which are not multiples of each other, and we saw that yes, okay, okay, the vector space containing these two vectors is able to span all of R2. Okay, spanning all of R2, that means all the vectors of the size 2 cross 1, that is xy, can be represented as the linear combination of these two vectors v1, v2 or c1, c2, whatever you name it as. Let me name it as c1, c2 here only. This was c1, this was c2, and whether c2 is equal to some scalar times c1, no. Okay, no, c2 cannot be written as kc1. Okay. No, you cannot say less. They are coming, every now and then. So you should know the concept of that vector space for EC, Harshraj. Okay, vector space or span, basis in any of the format question can come to you. Okay, so you should not neglect it. Now, next I took an example, vector space V, okay, containing two vectors C1 and C2, where C1 is equal to 2C1. That means the given two vectors are scalar multiple of each other. Okay, the given two vectors are linearly dependent. They are not independent, and they are not able to span all the vectors of R2. Does V span R2? We found the answer no. So I told any two vectors which are linearly independent will be able to span all of R2. Similarly, any three vectors in R3 which are linearly independent will span all of R3, or in general, any n vectors in Rn. Okay, any n vectors in Rn that are linearly independent will span all of Rn. Okay, that means to span a vector space Rn, you need n independent vectors in Rn. Okay, but how do you identify any given vectors are dependent or independent? How do you identify whether two vectors in general, now generalizing it, okay, vectors are dependent or independent? Suppose you are given p random vectors v1 to vp. Okay, v1 to vp. Okay, all the vectors, okay, belong to Rn. Okay, that is they are of the size n cross 1. Okay, that is of the size n cross 1. Okay, and there are p such vectors. But what does it mean that the vectors are dependent? That means there is some equation like a1 v1 plus a2 v2 etc up to av vp equal to 0. If there is any such relation, then you can express. Okay, then you can express now vp is equal to something. It is equal to minus 1 upon ap a1 v1 plus a2 v2 etc. Any one vector can be expressed as the linear combination of the rest. So vectors are linearly dependent. If there is no such equation, then the vectors are independent. Now, before I tell you official method, think again. Okay, taking the example of this, what I told you. Okay, what I told you here, x belongs to the span of v1, v2 means x is a combination of v1, v2. That means if x is a combination of v1, v2, that means the third column becomes dependent on the other columns, and whenever there are dependent columns, the determinant must be 0. The determinant must be 0. Okay, taking the motivation from this example, before I show you the official method, let me write down three random vectors. Okay, let me write down three random vectors. Okay, suppose I write down a vector. Okay, yeah, let's consider this vector. Let us consider this vector. Okay. My question is whether the vectors x1, x2, x3 are linearly independent. Okay. Second question, another way of asking the question. Okay. Does the set X containing these three vectors x1, x2, x3 span all of R3? Okay, these are two ways of asking the question. Okay. Yeah, definitely vector integral questions are important and more important. Harshraj, yes, definitely. Okay, so now whether the vectors are linearly independent or not. Okay, what can be the method? See, simple ways. I'll put down a matrix A. I'll form a matrix A. Okay, I'll form a matrix A such that the columns of the matrix are the given three vectors. Such that the columns of the matrix are the given three vectors x1, x2, x3. x1, x2, x3. Clear? Are the given three vectors x1, x2, x3. Okay. So what is this matrix? 1, 2, 0, 0, 4, 6, and 2 and 8 and 4. 2 and 8 and 4. Okay. So now what is the determinant of A? Determinant of A. So let's calculate the determinant. 1 into 4, 4, 16 minus 6 into 8, 48. Okay. Then minus of 0. Then plus of 2. Okay, 12 minus 0. So how much is this determinant? This is minus 32 and plus 24. Okay, we have the determinant which is not equal to 0. Now, suppose if determinant was 0, what does it mean? If the determinant was 0, what does it mean? If the determinant was 0, what does it mean? It would simply mean that the columns are dependent. Then only determinant would go 0. Here it is non-zero. And because it is non-zero determinant, that means the columns, you can think with rows or columns, anything. Let me explain with columns right now. The columns are independent. Now, what are the columns? What are the columns here? The columns are respectively, okay, the columns are respectively the given vectors. C1 is x1, C2 is the x2 vector, C3 is the x3 vector. Is that clear? Okay, is that clear to everybody? Okay, that means columns are independent. That means the given vectors x1, x2, x3 are independent. So are the vectors x1, x2, x3 independent? Yes. Before I write down the answer, let me do a small change in the question. Let me copy the same slide. Yeah. Let me first come up here. Okay, are the vectors x1, x2, x3 independent? Yes. Yes, they are independent. Are they independent? Yes. Okay. Does the set x1, x2, x3 span all of R3? Yes, because what I just told you, okay, any three vectors in R3 which are linearly independent can span all of R3. So yes, the second statement is also correct. Okay, now, okay, this is about the first question. I have changed, I'll go to the question once again. I'll change a small data here and I will repeat the calculations. What is the small change in the data? Let me make it 6. And now let's see the results. Before I see the result, okay, let me do the changes here. See, once again, same procedure. A small change in the number has been done. Okay, once again the same procedure. I'll form the matrix A with the given vectors x1, x2, x3. What are x1, x2, x3 will become the columns of the matrix. So 1, 2, 0, 0, 4, 6 and 2, 8 and 6. Now let's calculate the determinant once again. So see, once again, starting from fresh, 1 into 4 into 6, 24. Okay, minus 8 into 6, that is 48. Okay, minus 0 and plus 2 times 2 into 6, 12 minus 0. Okay, so this is minus 24 and 2 into 12 is 24, 0. Now, determinant of the matrix turned out to be 0. Determinant equal to 0, and that is only possible if somehow the columns are dependent on each other. How they are dependent, I do not care. But if the determinant is 0, that means 100%, okay, the matrix has dependent columns. That means x1, x2, x3 are dependent. So are they linearly independent? No. Then does the set x equal to x1, x2, x3 span all of R3? No. Only three linearly independent vector can span all of R3. So this also is no. Both answer will be either yes or both answer will be no. Is that clear, everybody? Okay. Right. Now, the next point. Okay, this is the same procedure I have noted here. Okay, so with respect to three vectors, form the matrix, and if the determinant, if it is 0, then the vectors are linearly independent. Non-zero, then it will be independent. Okay, or if there are the vectors v1, v2, if suppose, first let me write down here, suppose you have the vectors v1, v2, etc. up to vp, okay, which belongs to Rn. That means they are the vectors of the size n cross 1. Okay, but suppose p vectors are given. So what type of matrix will be formed? Every vector has n elements because it is belonging to Rn, and there are p such vectors. It is n cross p. These vectors will be independent if the rank of A is equal to p. Okay, because maximum how many independent vectors? Maximum how many independent vectors? Okay, how many independent vectors? Maximum p. There are p vectors, na? Or maximum all p can be independent, not more than that. Okay, so if all p are independent, then rank of A should be equal to p, because rank is equal to number of independent columns. How many columns are there? P columns are there. P columns are there. Of course, I've assumed that p less than n. Of course, I've assumed that the p is less than n. P is less than n. Okay. P is less than n. Okay, P is less than n. Okay, right, P is less than n. Now, what I was telling you, let me go back once again. Okay, so let me go back once again to the same definition, that any three vectors in R3 that are independent, that are linearly independent, will span all of R3. Okay, that is the reason in the first example, in this question, okay, the three vectors x1 and x2, x3, okay, they are linearly independent. Yes, okay, because determinant was non-zero. And because they are linearly independent, they are able to span all of R3. Okay. In the second case, the vectors are not linearly independent. They have some dependency. Determinant 0 means some dependency is there. Okay. And then, does the set X belong X containing the vectors x1, x2, x3 span all of R3? That also is no. Okay. Now, this here is going to come to another important definition, that is known as the basis of a vector space. What do you now mean by the basis of a vector space? Next important concept. Okay. Now, consider the vectors v1 to vn, which are some vectors in Rn. Then these vectors are said to form a basis of Rn if the vectors are v1 to v1, v2, etc. up to vn, okay, are linearly independent, and every vector in Rn can be expressed as the linear combination of the vectors v1 to v2. That means, let me put it more simply. Okay, let me put it more simply. Okay, consider this basis set. We define it as a basis set. Okay, suppose B, v1, v2, etc. up to vn. This is said to be a basis set. Okay, this is said to be a basis of V. This is said to be a basis of, okay, of which vector space? Of Rn. I'm talking generally with respect to Rn. If what I told you, let me rewrite once again. If v1, v2, etc. up to vn are linearly independent, let me write it in short. If the vectors are linearly independent and every vector in Rn can be expressed as linear combination, that means what? That means this set B, okay, this set B spans Rn. Okay, this point I have explained you earlier. Vector B spans Rn. What does it mean? Or Rn is spanned by V. What does it mean? That every vector in Rn should be represented as the linear combinations of vector in B. That is what this point is telling. Every vector in Rn can be expressed as the linear combination of which vectors? Of the vectors inside B, v1 to vn, v1 to vn. That means, again going to the previous example. Okay, what is that previous example? Where is that previous example? This one. Okay, here the three vectors are linearly independent. Okay, here these three vectors are linearly independent, and hence they can form a basis of R3. Okay, hence they can form a basis set. Let me write it here clearly. Hence they can form a basis pair. So what can be the basis set B? x1, x2, x3. Okay, so what is the basis set? What is the basis set? I repeat, there are two conditions. Number one, the vectors inside that set, okay, should be linearly independent. So are these three linearly independent? Yes. Okay, then second, these three vectors, okay, should be able to represent all vectors in Rn by the linear combination of x1, x2, x3 or vice versa. Okay, all vectors of Rn, here it is R3 example, all vectors of R3 should be linear combination of x1, x2, x3. So that also I told you, does the set X span all of R3? Yes. Okay, because it span all of R3, then it is a basis set. So there are two conditions, okay, for a set to be basis set. Now, number one, all the vectors inside the set should be linearly independent. And every vector of Rn, here it is R3, every vector of R3 can be expressed as a linear combination of the vectors inside this basis set. Okay, if these two conditions are met, then the set is a basis set. So in the next question, okay, there is a question number 3 I will add. Okay, there is a question number 3 I'll add. Is the set X a basis of R3? My answer is this also no. Because for it to be a basis of R3, all the vectors inside the set X must be linearly independent. All the vectors inside the set must be linearly independent. So are all linearly independent? No. Okay, so these are the three things you should be connecting. Vectors being dependent or independent, whether they span R3, whether they form a basis of R3. Whether they form a basis of R3. Whether they form a basis of R3. Okay. So, from this example, from these examples, if I generalize, okay, if I generalize what I say, okay, what can I say? Okay, what can I say? Suppose V1, V2, V3, etc., Vn, okay, let these vectors be n linearly independent, n linearly independent vectors in Rn. Okay. Okay. Be n linearly independent vectors in Rn. Or suppose, let me simply say, these are some n vectors. Okay. Be n vectors in Rn. Okay. If these all are linearly independent, then what can I say? If these are linearly independent, then number one point, they span, repeatedly I have told you this point, they span all of Rn, and number 2 point, okay, they also form a basis of Rn. They also form a basis of Rn. Okay, the same point I told here also. Let me go back. Let me keep going back and keep relating the things. What I told you here, any n, first again, any three vectors in R3 which are independent will span off all of R3. Then I generalized and I explained you that any n vectors in Rn, not any n vectors, but which n vectors, any n vectors which are linearly independent will span all of Rn, and hence form a basis of Rn, and hence form a basis of Rn, and hence form a basis of Rn. That is what I have written here in other way. Okay, so if there are, let me go back here. If V1 to Vn be n vectors, if they are linearly independent, first of all, if they are dependent, so nothing will follow here. Okay, if these are linearly independent, then they span all of Rn and they form a basis of Rn. They also form a basis of Rn. Okay, so same thing I have explained here. Okay, if there is a set of n linearly independent vectors, and if there is every set of n plus 1 or more vectors in V which is a linear dependent, okay, that means every other vector should be a linear combination of these independent vectors. Okay, then the V is said to have dimension n and is written as dimension V equal to n. So what is the meaning of this dimension? Okay, what is the meaning of this dimension? Okay, dimension means the maximum number of linearly independent vectors, okay, in a given vector space, right? So suppose if there is a vector space Rn, as I told you, the dimension n. Now here comes the true definition of dimension. Dimension, by dimension in the beginning only I told you dimension doesn't mean the size n cross n. What I mean by dimension? By dimension I mean that this vector Rn can have a maximum of n linearly independent vectors, okay, that can form a basis of Rn, and hence the dimension of Rn can be n. The dimension of R3 can be 3. The dimension of R2 can be 2. Okay, can be 2. Okay, now let's take a numeric question here. Let's take a numeric question here. Okay, the set 1, 2, 2, 2, 1, 2, 2, 2, 1 of vectors is what? Is linearly independent and forming a basis of R3. Linearly, see, first of all, the vectors being linearly dependent and forming a basis, not at all possible. The vectors being independent and not forming a basis, 3 vectors being independent and not forming a basis of R3, also not possible. Okay, now if the 3 vectors are independent, they will form a basis of R3 because this is 3 vectors, same thing, na? Okay, if there are n vectors and if all of the n are linearly independent, then they form a basis of Rn. Similarly, if there are 3 vectors, okay, if they are independent, they form a basis of R3, or other way, if they are dependent, they will not form a basis of R3. So it is either A or D. That means to choose either out of A or D, you have to just say whether the vectors are dependent or independent. For the vectors to be dependent or independent, what you need to check? For the vectors to be dependent or independent, I told you, na, what you need to check, because 3 vectors and 3 cross 1 size, so you can just go to the determinant of A. Which A? Okay, where the vectors are arranged as the columns 1, 2, 2, 2, 1, 2 and 2, 2, 1. Check the determinant of this simply. Okay, so it is 1 and 1 minus 4, minus of 2, 2 minus 4 and plus of 2, 4 minus 2. Okay, this is minus 3, 2 minus 2 into minus 2 plus 4 and 2 into minus 2 is minus 4. Okay, it is not equal to 0. What I am getting, that determinant is not equal to 0. That means the columns, okay, are independent columns, because if there were any dependency in the columns, okay, we would have got the 0 determinant. Independent columns means, what are the columns here? The given vectors. Okay, the given vectors are independent, linearly independent. Okay, and if they are linearly independent, they will form a basis of R3. Option number A. This is how you have to check. Option number A. Okay, next question. Okay, if the set K11, 0, 1, 1, K0, K of vectors form a basis of R3, then K is not equal to what? Then K is not equal to what? K is not equal to what? Now they form a basis of R3. 3 vectors, they form a basis of R3. Okay, if the 3 vectors, suppose I call it as x1, x2, x3. Okay, if x1, x2, x3 are, they form a basis, so they must be linearly independent. That means the determinant of A, where A contains the columns as x1, x2, x3, should be equal to, not equal to 0, because if determinant equal to 0, then we have dependent columns. So if I want independent columns or independent vectors, the determinant not equal to 0. That is why the question also reads like this: K not equal to what? Okay, so K11, okay, 0, 1, 1 and K0, K, this is not equal to 0. Okay, so K, okay, into K minus 0, okay, minus 0 and then plus K into 1 minus 1, this is not equal to 0. So what I am getting, K square, this is 0, this is also 0, K square not equal to 0, that means K also is not equal to 0. Okay, so K is not equal to what? K is not equal to 0. For the 3 vectors to form the basis, K should not be equal to 0. K can take any value but not equal to 0. K can take the any value but not equal to the 0. Okay, but not equal to the 0. Next question. See, GATE 21 1 mark question. If the vectors are in R3 are linearly dependent, simple question, direct question. GATE 21 1 mark. If the given vectors are linearly dependent, what is the value of x? 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 Let's do it. What is the value of x? What is the value of x? Yeah, do it, guys. This is simple only. Please do it quickly. Just please do this quickly. Just please do this quickly. This is simple one only. Okay, let's do it simply. Yes, dear. Do it quickly. Yeah, let's check it out. Simple question. Let's check it out. This is a simple question. Okay, so linearly dependent. That means if I form, okay, the determinant of the matrix A such that the matrix A contains the columns as 1, -1 and 2. Okay, 7, 3, 0. Okay, whether they give you as a row vector doesn't matter. You write them as column, doesn't matter. A and A transpose always have the same determinant. A third is 2, 3, 1. Okay, this determinant must be 0. Dependency means dependent columns. Okay, determinant must be 0. So solving it, 1 into 3 minus 3x minus of 7 minus 1 minus 6. Okay, plus of 2 minus x minus 6 equal to 0. Okay, let me solve it now. 3 minus 3x minus 7 into minus 7 is plus 49, and then minus 2x and then minus 12 equal to 0. So total of 5x on the right side, 49 plus 3, 52 minus 12 is equal to 40. So x should be equal to 8. Okay, x is 8. Okay, the value of x is then equal to 8. Yes, we have some correct value from Bhanu Teja and Suraj Kumar. Yes, it is going to be 8. Okay, simple question, na? Simple question. Yes, absolutely simple question. Nothing to worry. Okay, nothing to worry. Now, next, if the vectors even, GATE 16 2-mark question. Okay, if the vectors even, that is 102, E2 equal to 010, E3 equal to minus 201 form an orthogonal basis of the three-dimensional real space R3, then the vector U. See, if the vectors, let me tell you one more point here. Okay, if the vectors are orthogonal, okay, they will automatically be linearly independent. I need not prove it right now. Okay, but yeah, if three vectors, okay, if three vectors in R3 are orthogonal, means perpendicular to each other, okay, they will also be forming the basis because they will be linearly independent. Okay, so let me write it here. Okay, if the vectors are orthogonal, okay, they will also be linearly independent. Okay, and if they are linearly independent, they can form a basis. So that is why they clearly mention, okay, the vectors E1, E2, E3 form an orthogonal basis of the 3D real space R3. Then the vector U can be expressed. Now see here, sometimes it's a 2-mark GATE 16 question, IISc Bangalore paper, but here it is more or less like an aptitude question. Even if you don't know the meaning of orthogonal basis, vector space, R3, if you even don't know anything, you can still, match your options and see what you have to specify. There is a given vector U which has to be expressed as linear combination. Okay, so any vector other than these three. Okay, because these form a basis. That means they span. If they form a basis, so these three vectors E1, E2, E3. Okay, what can I say? The E1, E2, E3, because they are linearly independent, okay, they span all of R3. That means any vector in R3, U, suppose is any vector in R3, okay, should be represented as linear combination, okay, A1, E1, okay, plus A2, E2, plus A3, E3. Correct, na? Okay, so still if you don't know what is spanning, what is R3, what is basis, still what you can logically solve aptitude question given E1, E2, E3, how you can express U in terms of E1, E2, E3. You can match the options yet. Okay, so what is the requirement here? Okay, what is U? Now let me solve it here. What is U given to you? 4, 3, minus 3. Okay, should be equal to A1 into E1. Okay, A1 into 102. Correct. Plus A2 into the E2. What is the E2? Is 010. Okay. The calculations also will appear simple because many elements are 0. Plus A3 into E3 minus 2, 0 and plus 1. Okay. That means 4, 3 minus 3 on the left side equal to right side. What is the simplified expression? A1 into 1. Okay. That is A1. Second 0 and then minus 2A3. Second element 0 plus A2 plus 0. So second is only A2 and third 2A1. Okay, third is 2A1 and plus A3. Okay, dear, from here you are able to conclude second to second element A2 equal to 3. That means option number C or D. That is very clear. A2 should be equal to 3. Okay, then A1 minus 2A3 should be equal to 4 and 2A1 plus A3, the last one, 2A1 plus A3 should be equal to minus 3. and a1 minus 2a3 should be equal to 4. Okay, so to solve this now, okay, from here what will I get? Suppose I multiply the second equation also by 2, okay, and then add. So 2a3 minus 2a3 cancel. This you multiply by 2. So 5a1 is equal to minus 2. Am I right? Minus 6 plus 4. So a1, okay, a1 is minus 2 by 5. Minus of 2 by 5. Yes. So option number C and D. Okay, both have minus 2 by 5. So better. Okay, what is the a3? For the a3, to form a3, now multiply this equation by 2 and then subtract. If you multiply this equation by 2, to a3, and then if I subtract here, minus 2. So 5a3 is equal to, here I multiplied by 2, minus 3 minus 8, minus 11. Okay, minus 11 by 5. So option number D. Okay, minus 11 by 5. Minus 11 by 5. Option number D. Okay, it's option number D. Minus 11 by 5. Okay. Let me once again recheck the calculation. Minus 2 by 5. Minus 2, so minus plus 22 by 5. This becomes how much? 20 by 5. And that should be 4. Yes, it works. Option number D it is. Option number D. Got this? Okay, so vector E1, E2, E3 form a basis of R3. That means E1, E2, E3 are linearly independent. Okay, and they span all of R3. That means any vector in R3, any other vector U in R3, okay, should be represented as a linear combination of the given vectors E1, E2, E3. That is the concept. But again, I'm telling you, some questions are very logical, just like aptitude. You can match the option still if you don't know the concept here. Okay, next question. Next question here. Now see here. Let X belong to R3. Okay, given by, okay, so let X as a set belonging to R3 given by X, Y, Z such that X plus Y plus Z equal to 0. See, I have taken this condition earlier also. X plus Y plus Z equal to 0, plane passing through. I have explained you this in the beginning. Okay, I am putting that question as a MCQ question now, but this X plus Y plus Z equal to 0 is the equation of plane passing through origin. Through origin 0, 0, 0. Okay, consider the vectors v1 and v2 given to you. 1 minus 1, 0, 1, 0 minus 1. Similar to vectors I have taken earlier also. My first option is X is not a subspace of R3. Okay, it is a subspace of R3. You can just, this plane passing through origin is a subspace of R3. It is a subspace of R3. Why? Just rewind the video, go to the beginning and you will understand why. It is a subspace. Okay, so this is false. We have to choose the correct option. Okay, then V equal to, there is a set of V1, V2. Okay, now whether the set is linearly independent set but it does not span X and hence not a basis, or V1, V2 is a basis of X. V1, V2 is a basis of X. Now see here. Okay, can it span R3? Okay, can it span not R3, sorry, can it span this given vector X? Can it span this given vector X? So how to check whether it can span the given vector X or not? I told you, and once again I will form a matrix A. Okay, where I'll put down the vectors v1 and v2, 1 minus 1, 0. The v2 is 1, 0 minus 1, 1, 0 minus 1, and the set S, the vector X, okay, which is given by X, Y, Z such that X plus Y plus Z is equal to 0. Okay, this is v1, this is v2, this is X. Okay. Now listen to me. Okay, is the rank of the matrix, can the rank of the matrix be calculated here? Can the rank of the matrix be calculated here? Can the rank of the matrix be calculated here? So what will I do is, a simple operation let me do here. Okay, let me replace, dear, R3, okay, by R1 plus R2 plus R3. Okay, then how the matrix will look like? Okay, 1, 1, X, minus 1, 0, Y. Okay, and 0 plus minus 1 plus 1, okay, will be 0. Minus 1 plus 0 plus 1, again 0. Z plus X plus Y. Z plus X plus Y plus Z. Okay. But which is 0 only. Okay, which is 0 only. That means entire third row is 0. This also will become 0. Na? X plus Y plus Z equal to 0. So entire third row is 0. Okay, entire third row is 0. That means every 3 cross 3, there is only one 3 cross 3 minor, and that is 100% 0. Okay, 100% 0. Okay, that means that means the rank of the matrix is not equal to 3. Okay, now let me check any 2 cross 2 minor, 1, 1, minus 1, 0, and check the determinant. 0, minus, minus, plus 1, and the determinant is, and the 2 cross 2 minor is non-zero. If you have at least one 2 cross 2 minor which is non-zero, rank of the matrix is equal to 2. Now, if the rank of the matrix is 2, okay, if the rank of the matrix is 2, it means that the matrix has 2 independent columns. 2 independent, linearly independent. Independency means we are talking about only linear dependency, linear independency. It has 2 linearly independent columns. That means it has only one dependent column. It has only one dependent columns. Are the V1, V2 dependent on each other? How to check whether V1, V2 are dependent on each other? See dear. Okay, if they were dependent, okay, if two vectors are dependent, if they are multiples of each other, okay, so 1 into 1. But what to multiply minus 1? Do you have any scalar number? When you multiply by minus 1, it gets converted to 0. Only possibility is 0, minus 1 into 0. But if you multiply the 0 here, 1 into 0, this also should be 0 and this also should become 0. That means there is no scalar number, okay, which can relate V1 and V2. Okay, so it has only one dependent column, and I can say that V2 cannot be written as KV1. That means the possibility is X can be written as, okay, the possibility is the third column may be dependent and it can be written as something like A1 V1 plus A2 V2. Okay. Acha, one more thing I told you. If you get a fixed value of rank, one more thing I told you earlier, just watch the video once again if you have missed the beginning part. If the rank turns out to be fixed, then spanning will occur. If the rank is not fixed, then spanning will not occur. I've told you 2 different cases earlier. Okay, so here X is equal to A1 V1 plus A2 V2. That means the set S, okay, every vector in the set X can be represented by a linear combination of V1 and V2. Okay, so now can I say that V, okay, span X? Yes. Okay, that means, okay, here the set V, okay, which contains V1, V2, spans X, okay, and hence a basis of X, and V1 and V2 itself are also independent to each other. Okay, so see, option number B, V1, V2 is a linearly independent set. Up to this part is okay, but it does not span X and not a basis. This part is wrong. Okay, because V1, V2 also are linearly independent, they span X and hence they are a basis of X. Option number C is correct. Option number C is the correct option. Okay. Okay, this plane passing through origin is a subspace of R3 explained earlier. So you can watch the video, beginning part of the video where I have taken that plane picture. I've shown you that plane passing through origin. Okay, dear. Okay, next. Another question. Yeah, this one, a good means pure conceptual question. GATE 2021 mark. Okay, if V1 to V6, are 6 vectors in R4, then which of the following statement is false? Option number A. It is not necessary that these vectors span R4. Okay, see. What vectors can span R4? Okay, first of all, to span R4, what is enough? If you have 4 linearly independent vectors, but here 6 vectors are given. But what are 6 vectors? Okay, maybe the vectors are in the form of V1, okay, 2V1, values are not given. No? Maybe the next vector is 3V1, next is 4V1 and etc. All are only dependent on V1. It may be possible, out of the 6 given, it may be possible, only one independent. Okay, and to span R4, you need 4 independent vectors. So we don't have the enough information. Okay, so it is not necessary that these vectors span R4. True. Okay, second. Okay, these vectors are not linearly independent. See, in R4, okay, maximum, what is the dimension? See, if you talk about R4, the dimension of R4 equal to 4. Okay, that means maximum 4 linearly independent vectors. Okay, so these vectors are definitely not linearly independent. Okay, this is a true statement because only maximum 4 out of it, only maximum 4 out of it are linearly independent. Rest 2 can be dependent. I don't say any 4 out of this will be independent because the vectors are not given. But let's say even if some random vectors are given, max to max 4 out of this can be independent. 4 out of this can be independent. Rest 2 can be dependent. Rest 2 can be dependent. Clear? You understand once again like this, na? You understand once again like this. You form a matrix containing the vectors v1 to v6. Okay, what is the size of this matrix? So v1 to v6 are vectors in R4. That means all of them has 4 elements. So there are 4 rows. But how many columns? 6 columns. Okay, so rank of A less than equal to 4. Rank cannot be greater than 4. That means maximum 4 dependent, maximum 4 independent columns. Even if the rank is 4, rank of A maximum value is 4. That means maximum 4 linearly independent columns. That's why telling you maximum 4 linearly independent vectors if there are vectors given in R4. Okay, so whether these vectors are not linearly independent, true. All 6 cannot be linearly independent. Max to max 4 out of this can be linearly independent. Ask me if you have any doubt. So this is true. We have to find the false option. Any 4 of these vectors form a basis. How can 4 vectors form a basis? Okay, there are 2 conditions to form a basis. The 4 vectors must be linearly independent and they should span all of R4. But since the vectors are not given, okay, how can I confirm say that any 4 out of these vectors, okay, this is true, okay, this will be true if any 4 of these vectors, if any 4 of these vectors are linearly independent and span all of R4. Okay, but we can't say here, okay, whether the 4 vectors are linearly independent, okay, whether the 4 vectors are linearly independent, we can't say. We can't say. So this option, they say that any 4 this will be independent, any 4 this will form a basis. No, it can't say. That is the false. That is what is the false. We can't say actually. So that is why we have to put it as a false statement. Okay, let's read the D. If V1, V3, V5, V6 span R4, then it forms a basis. That is correct. See, what they say, if V1, V3, V5, V6 span R4, okay, that means they must be independent also if they are spanning R4. Okay, okay, then they form a basis of R4. This is true. This is definitely true. Okay, if 4 vectors span R4, okay, so those 4 will be independent, and using those 4 independent vectors, we can write down all the vectors in R4, and then, okay, because they are independent also, they form a basis of R4. Okay, 4 vectors being independent spanning R4 automatically forms the basis, set. So these are all connected only. These are all connected. So D is also true. Which of the options is false? C. We cannot generalize here. They said it as a statement. Any 4 of these vectors form a basis. False. Any 4 of these vectors form a basis. False. Okay, false. Right? So this is what is the correct observation. Okay, this is what is the correct observation. Okay, now, okay, since you have learned about vector space, okay, the span and the basis, vector space, span and the basis. Okay, we have also taken some, GATE conceptual PYQs asked with relevance and with reference to this topic, isn't it? With reference to this topic. Hope these topics and these ideas are clear to you. Okay, when you go to, all these concepts are further linked with the linear system of equation. How they are linked with the linear system of equation? Just for an example, if I explain you a calculation, linear system of equation, AX equal to B. Now, first of all, understand, okay, when you talk about linear system of equations, just to give you an idea, I'm not going to go into linear system of equations in this class. That is another entire big story. Okay, okay, linear system of equation. Okay, AX equal to B. First of all, what do you mean by this operation AX? What do you mean by this operation AX? Understand here, what do I mean by this operation AX? Suppose, let me take any matrix A here. Okay, any matrix A here. Okay, into vector x. Okay, now for a moment, okay, let's take this vector x is equal to containing some numbers a1, a2, a3. Let's say they contain some numbers a1, a2, a3. Okay, let's say they contain some numbers a1, a2, a3. Okay, so then what is this x? Let me write down here. This is a1, this is the a2, and this is the a3. Okay, so when you solve this now, what do you get? See, you get 1 into a1. Okay, 1 into a1, 2 into a2, 2 into a2 plus a3. Next is 4 into a1 plus 5 into a2, okay, plus a3. And then you can write it as 3a1 plus 6a2 plus 5a3. Okay. Now this is also equivalent to now, okay, a1, a1, a1. Okay, let me take a1 and then let's write this one. Let's separate the columns 1, 4, 3. Okay, then this can be written as a2 into 2, 5, 6 and plus a3 into the, what is the a3? 1, 1, 5. Okay, now dear, if you observe, okay, now dear, just try to observe. What is this? This is the column 1 of the matrix. This is the column 2. This is the column 3. Okay, so you have a1 c1 plus a2 c2, a2 c2, okay, plus a3 c3. That means what is this operation a into x is doing for you? What is this operation a into x doing for you? A into x is expressible as a1 c1 plus a2 c2 plus a3 c3. That is forming all the linear combinations of, okay, all the linear combinations of, okay, linear combinations of the columns of A. Linear combinations of the columns of A. Okay. Linear combinations of the column of A. Okay. That means if I say Ax equal to B, when I write down the equation Ax equal to B, or that means B which is equal to Ax, which is containing all the linear combinations based on A1, A2, A3, okay, containing the linear combination of the columns of A is said to be defined as the column space of A. Is said to be defined as column space of A. What do you mean by column space of A? Okay, what is the column space? Okay, this is related for linear system of equation. Just very brief terms I am telling. I am not going to the linear system, but yeah, you can note down separately. What do you mean by column space of A? Column space of A, space as you know is a set of vectors. The column space of A is the set of vectors which contains the linear combinations of the columns of A. Okay, or I can say that it spans the columns of A. It spans the column of A. Correct. So B is the column space. B equal to Ax basically means the column space of A. Okay, is the column space of A. Okay, that means B spans C1, C2, C3. That means B must be a linear combination of C1, C2, C3. B must be a linear combination of C1, C2, C3. Now, because B is a linear combination of C1, C2, C3, okay, when I form the matrix A is to B, when we form the matrix A is to B, what is the A is to B? C1, C2, C3. A has the 3 columns C1, C2, C3. Then there is a column of B where B is further expressible as A1, C1 plus A2, C2 plus A3, C3. Okay, so this system is only solvable, okay, if Ax, the system of equation Ax equal to B or B equal to Ax. But what is Ax? Column space of A. What is Ax? Ax contains linear combination of columns of A. And if you say Ax equal to B, that means B also contains the linear combinations of the columns of A. That means I can write down B equal to A1 C1 plus A2 C2 plus A3 C3. Okay, that means if B is not equal to this, then the system is not solvable. Okay. If B is not equal to A1 C1 plus A2 C2 plus A3 C3, okay, Ax not equal to B. Okay, system of equation Ax equal to B has no solution because Ax cannot be equal to B. The system of equation Ax, okay, equal to B has no solution. But on the other hand, if B equal to A1 C1 plus A2 C2 plus A3 C3, then we can clearly say that Ax, because this is what is Ax and this is B, so Ax equal to B is solvable. Ax equal to B is solvable. But because B is a linear combination of columns of A, so whatever is the rank of A, and whatever is the rank of A is to B. See, rank is the number of independent columns, I can say. Na? Rank is the number of independent columns, I can say. Listen to me very carefully. Rank is what? Rank is the number of independent columns. Suppose from here you have n independent columns. So from here to here also n independent columns, because this is already a dependent column. B is already a dependent column. So here if you have n dependent columns, or reverse, here you have n independent columns, from here to here also n independent columns. So that means whether you check the rank of this matrix A or whether you check the rank of the larger matrix A is to B, it will be same. Okay, rank of A equal to rank of A is to B, and this is what in mathematics we study as the Rauch's theorem. The system is solvable or the system is consistent if rank of A equal to rank of A is to B. Okay, but further, okay, if rank of A does not equal to rank of A is to B, okay, then the system has no solution, not solvable. Okay, now further in Rauch's theorem there are two conditions. Okay, if both the ranks are equal, okay, and just concluding, if both the ranks are equal and equal to n, number of variables, n is the number of variables, okay, let's say n is the number of variables. It may be 3 variable example very commonly, or any number of variables. If both the ranks are equal and equal to n, then the system has unique solution. It is solvable and it will only give one solution. And further, this can be understood, but yeah, I'm just writing the final conclusion. Rank of A equal to rank of A is to B. Both are equal for the system to be solvable, but both are less than n. The system of equations will have infinite solution. The system of equation will have infinite solution, right? Infinite solution. Okay, so that is what, all these discussions that you have done, okay, about vector spaces, dependent, independent vectors, ranks, all this are further extended and applied to the linear system of equation Ax equal to B. Okay, it is solvable if B can be represented as Ax. And what is the representation of Ax? Ax, okay, is the representation which is nothing but the linear combination of the columns, which is the linear combinations of columns of A. So if B is also the linear combination of columns of A, then the system of equation is solvable. Okay, this entire set containing all linear combinations of A is also defined as column space of A. Also defined as column space of A. Okay, also defined as column space of A. Correct. So this is one terminology, column space. Another important space, like I'm giving you some examples of vector spaces. This is one important vector space known as the column space. Another important vector space, if you talk about homogeneous system of equation, okay, homogeneous system of equation, Ax equal to 0, okay, Ax equal to null, where all the right side coefficients are 0. Okay, so the set of all non-zero, because 0 will always satisfy, but set of all non-zero linearly independent vectors x, the set of all non-zero linearly independent vectors x will form the null space of the matrix A. So there is another important space known as the null space, just defining, not going into detail. Null space of the matrix A. Okay, set of all non-zero linearly independent. See, because for linear system of equations, you can refer to my earlier videos. I have taken videos on linear system of equation, non-homogeneous and homogeneous. There, this null space concept, nullity, everything is covered. What is nullity then? Every vector space has a dimension. Nullity is known as the dimension of this null space. The dimension of this null space. Okay, then further how this homogeneous system is solved, thus, and then all such non-zero independent solutions are put inside a vector space. That vector space is known as the null space of the matrix A. Okay, so all this, what I'm trying to tell you is all that you have studied today, vector spaces, okay, and the concept of dependent, independent vector spanning, okay, like here B spans the column space, I could say. Okay. So all these are further extended and applied to linear system of equation. Okay, so all this vector space, span, basis, dependent, independent vector find a true application under the linear system of equation, and then also to the eigenvalue and eigenvector. Once again, dear, a quick reminder that the GATE 26 and 27 fresh online live course, okay, so that you can study at your place, okay, but still get the live interaction with the top faculties of ECEE. And yes, that batch starts from 8th of February, and the 1 year fee 19,999 for GATE 26, and for GATE 2027 the 2-year validity fee is 28,999. And yes, if you are interested to study in a competitive atmosphere amongst hundreds of students, finally in front of the faculty, okay, in a regular competitive atmosphere, you can join our first regular offline course for GATE 26. The first batch starts from 24th February. The fee is currently priced at 54,999. Also, guys, there are pre-recorded lectures available, okay, if you want to study at any time and at anywhere, at any part of the country. So you can also go for the pre-recorded courses for GATE 26. Okay, these are the different fees based on the validity: 3 months, 6 months, 9 months, and 12 months. Okay, all these recorded courses are available on the OM Online Plus app, which you can also download directly by this QR code. Okay, for GATE 27 also you can have the online pre-recorded lectures. Okay, with the validity of 18 months or 24 months. The fees is respectively mentioned here. Again, on the OM Online Plus app. And also, if you're preparing for AE examinations, so for AE examinations also online pre-recorded courses are available, so that you learn from anywhere, anytime, and the fee for 3 months, 6 months, and 9 months validity respectively for the AE pre-recorded online courses is mentioned here. Again, the platform will be OM Online Plus app, okay, where I have already shown you the QR code for the download app option. All right, dear. Okay, dear. So yeah, that's it. Okay, hope you have today understood the concept of vector space. Then what are vector subspaces? Okay, I told you there is some conditions for subspaces. Not every subset of a vector space is known as a subspace. There are some conditions, that additivity and scaling point that I mentioned. Then what is the vector? What is mean by spanning a vector set? What is the meaning of a vector span? What are independent and dependent vectors, and what is the basis of a vector space? What is the dimension of a vector space, and different questions and concepts around that were discussed. Okay, yeah, okay, that's it from my side. Bye bye, thank you, all the very best. The GATE EC examination is just nearly 1 week ahead. Today is 7th of February. You're going to write the exam on 15th February. Bye bye, thank you, stay safe, and keep preparing hard for your examination.